Hi. Today we are continuing our discussion of distributions of quantitative data, and we've discussed shape, center, and spread so far. Now we're going to add outliers, and part of outliers is also gaps and clusters, so we'll be discussing those. We are also going to talk about box plots today, which I'm sure you've done before, but we'll just quickly review those. So an outlier in statistics, it's a data point or points that are unusually small or large relative to the rest of the data. So it could be a piece of data that's far below the mean or far above the mean. Okay. A gap is a region of a distribution between two data values where there are no observed data. Gaps are interesting because we like to know why is there no data between these 2 points. And clusters are concentrations of data usually separated by gaps. And it's usually the outliers, the gaps, and the clusters that are the most interesting parts of a distribution. It's the unusual values that will spark our interest. So if you look at this graph below, it says, consider this graph of winning times for the Kentucky Derby horse race. Okay, here's a good example of outliers, a gap, and a cluster. So these are the winning times of every Kentucky Derby in seconds. Okay, so notice a very fast time. Someone finished in just under 120 seconds, so just under 2 minutes. You can see most people, and most horses it looks like, finish somewhere between 2 minutes and 2 minutes and 10 seconds. But look at this enormous gap right here. This is a gap, okay? That gap, no horses have ever finished between 140 and 150 seconds, actually about 155 seconds. Okay, so that's strange. Then we have a cluster of data over here, okay, where there's a bunch of times that are far longer than those times we saw in the beginning. And then we even have another gap and another time way out here, okay? Now overall, this distribution is, of course, skewed right, okay? And this would be a cluster. And these would all be considered potential outliers. We wouldn't really know for sure until we run a calculation on them, which I'm going to show you how to do shortly. But interesting, like, why is there a gap there? Why is there a cluster? I bet you could maybe guess if you know anything about horse racing. Sometimes the Kentucky Derby is run in the rain, okay? On years when it's dry, that's when we see this group of times, okay? And over here, these are when it was raining, okay? And this one, I bet, was super bad weather. Maybe it was very muddy. I don't know what the real story is behind that one, but obviously something really slowed that race down. It almost took a minute longer, than the usual times to finish. So the interesting thing is that those times in the cluster were from rain. So when we're looking at a distribution and we see gaps and clusters and outliers, we need to ask ourselves, why? How did we get that information? What's it telling us about Kentucky Derby race times? Okay. Now, there are 2 methods for finding outliers. Okay. And these are the 2 most frequently used in this course. Method 1, an outlier is a value greater than 1.5 times the IQR above the third quartile, or more than 1.5 times the interquartile range below the first quartile. So for that one, we would calculate the interquartile range, and then we would multiply it by 1.5. We would add it to the third quartile and subtract it from the first, and we would see if there are any values in our data that are outside of that range. Okay. We'll demonstrate that in a second. The second type of outlier is a value located 2 or more standard deviations above or below the mean. So in that situation, we'll find out what a standard deviation is for the data, double it, and then we'll add that to the mean and subtract it from the mean, and any data values that are outside of those points would be considered outliers. Okay. Both of these are valid methods, and we should be familiar with both of them. So first, let's use the method number 1, the 1.5 times the IQR method. Okay. So we're going to determine if there are any outliers in our state's visited data from earlier. So we're still using that state data since we're familiar with it. Here is the screen, which shows us the 5-number summary off our calculator. And we need that because we need the IQR. Okay. The IQR is, remember, is Q3 minus Q1. I got these numbers right from the chart there. And 18 minus 7 is 11. And then I'm going to take that IQR and multiply it by 1.5. And I have a calculator off to the side here. And that gives me 16.5. Okay. So now to find the outliers, what I would do is take Q3 from our screenshot, that was 18, and I would add 16.5 to that. Okay, I got that from over here. So 18 plus 16.5 gives me 34.5. That's going to help find outliers that are too large for our set of data. Then we're going to subtract that value from Q1. Q1 is 7, and I'm going to subtract 16.5. Now, obviously, 7 minus 16.5 is going to be a negative number. Okay, it's a negative 9.5. All right, so those numbers are called the fences. Okay, any data value that's outside the fences are considered outliers. So negative 9.5 is the lower fence, and 34.5 is the upper fence. Now, obviously, in our states visited data, we didn't have any negative numbers. Okay, no one saw negative 3 states. So there's going to be no outliers on the low end. Okay, none on the low end. But are there outliers on the high end? Well, here's our set of data at the bottom of the screen here. And any number above 34.5 would be considered an outlier. And of course, this data has 3. 35, 45, and 50. So 35, 45, and 50 are outliers on the high end. So usually we would make a comment similar to these two, where you'd say there's no outliers on the low end, but there are, in this case, 3 outliers on the high end, and we would list them out. Okay, and they're outliers because they are bigger than 34.5. Okay, and remember we got 34.5 by taking the third quartile and adding our 16.5 to that. And on the low end, obviously, we couldn't have any outliers because we didn't have any negative numbers. Okay, so you need to be able to do this by hand. Once in a while in the AP exam, they ask if there are outliers and they ask to show work. So we have to understand how this works. Let's see if there are outliers using the second method. Okay, and the second method was an outlier is a value located 2 or more standard deviations above or below the mean. So I get the mean from the calculator. I have the printout right there for our states visited data. I have our standard deviation, and we're going to use the population number, which is this one, because we'll call our class a whole population. And the standard deviation was 10.9. We'll just round to the tenths place. So remember, it's 2 or more standard deviations, so I'm going to double that standard deviation. So take 10.9 times 2. I get 21.8. Then I'm going to add it to the mean and subtract it from the mean. So the mean was 14.3, and I'm going to add 21.8. And I get 36.1. And then I'm also going to subtract 21.8 from the mean. So 14.3 minus 21.8. And again, I'm going to get a negative number here, which means there's no outliers on the low end, which same as before. So now those 2 values are considered our fences. So anything below negative 7.5 would be an outlier. So we have no outliers on the low end. And our other fence is 36.1. So anything above 36.1 would be an outlier. And we have two of those, 45 and 50. So 45 and 50 are outliers on the high end. Okay. Notice we didn't get exactly the same answer for both. Using the 1.5 times IQR gave us one more outlier using that method, and this method with the 2 standard deviations gave us 2 outliers. Either one is considered a valid method to find outliers, and they will usually specify in the question which method they wish you to use. Okay. Now, why do we care about outliers? Another reason, besides just their unusual points that we'd like to learn about, outliers can have effects on our calculations in statistics. Okay, so we have a term called resistant, and we also could use the word robust. But a measure is resistant or robust if it is not influenced by outliers. So if an outlier doesn't affect the calculation is considered resistant or robust. Non-resistant or non-robust is a measure that is influenced by outliers. Okay, so it's important to understand in statistics which terms or which calculations are resistant or robust and which are not. So the mean, standard deviation, and range are considered non-resistant or non-robust because they are influenced by outliers. The presence of outliers in the data will affect the values of these measurements. Okay, that is why in a skewed distribution where there are potential outliers, okay, we stay away from the mean and the standard deviation because they are affected by those. Okay, and also the range is affected by it. The median and IQR are considered resistant or robust because outliers do not greatly affect them or at all affect them usually. A quick example of this would be these two sets of data, the numbers 1 through 5 and the numbers 1 through 4 and then 50. Okay, 50 is an outlier in this case. Okay, so if I found the mean of both of these, the 50 would greatly affect the mean in this problem, and there is no outlier in the first set, so it would not affect the mean. If you look at the range in this first set would be 4, and the range in the second set would be 49, greatly affected by that outlier. But the median, which is supposed to be not affected by the outlier, the median of the first set would be 3, because that's the middle value. And the median of the second set would also be 3, because that is the middle value. You could change this 50 to be 500, and it still doesn't affect that the median was 3. Okay, so the median is not affected by outliers because it's really a position measurement, and the same with the interquartile range, not affected by outliers. Okay. Now, the other thing I said we were going to talk about today are box plots. And this is called graphing summary data. So here's the calculator screen of the 5-number summary from our states visited data. Remember, it's the minimum, the quartiles, and the maximum. So a box plot is just a graphical representation of this 5-number summary. Okay, and it can also identify outliers. So when you're making a box plot, the first thing you need to do is make an x-axis. Okay, and we need to scale that axis to include all of the data. And the data runs from 1 to 50. So maybe we could start at 0 and count by tens on our x-axis. Okay, and I made it a little longer than I needed to. But you make your x-axis first. Then we draw in lines for the min and the max. So the minimum's at 1, so I'm going to put that here, and we usually label the points above. And the max is at 50. So I'll label that up here. Both of those are lines. Then we make another set of lines at the quartiles, so 7 and 18. So quartile 1 is 7. Again, I'm going to write that in. And the third quartile is 18. I'm going to write that in. The first and third quartiles are what form the box of the box plot. Okay? And then we can connect those to these, the lines for the min and max, and those are called whiskers. Another name for a box plot is a box and whisker plot. And then the median gets drawn inside the box. So the median's at 11, and make another line right here. That is a box and whisker plot. Now, sometimes we include outliers in our box plot. And when we do that, I'm going to label this box plot, that's called a modified box plot. Okay? And if you remember from a previous slide, there were 3 outliers in our states visited data, but they were on the upper side of the graph. So if I was going to do a modified box plot, and I'll do that in red right here, I would show the minimum, the first quartile, the median, the third quartile. But for the presence of outliers, and our outliers were at 35, 45, and 50. That was using the IQR times 1.5 method. So I would make a star at one outlier. I'd make a star at the other one. And I'd make a star at 35. And you can make any symbol you want. It could be a square, it could be an asterisk, however you want to mark them. But we would mark the outliers with symbols like that. And then the first piece of data that's not an outlier, which I looked back and it was at 26 was the next number. At 26, that is where I would draw the upper whisker. Okay? So that's a modified box plot, where in a modified one, we show the outliers, and then the whisker on the right goes to the first value that's not an outlier. Okay? So the first value under 35 was 26. Okay? So in our course, when I ask you to do a box plot, I'd like you to show the outliers. So we will do the modified box plot. Okay? So something to think about here. At the bottom, the box represents the middle 50% of the data. Okay? So that means in this box above, I know that there's 50% of all of the data. Okay? And remember, the box is also a graphical representation of the IQR. Okay? The box is the IQR. All right? The line's whiskers extend from the quartiles to the most extreme point that's not an outlier. And outliers are indicated by their own symbol beyond this. So we already showed that. Your calculus. Okay. You would start by entering the data into L1, like usual. Go to stat plot. This is the screen you'd see. The box plot options are these two. And if you look, the calculator does both. It does regular box plots, so that's the one I highlighted in this first picture. And then it also does modified box plots. And if you look, you can see 2 little dots on the part that's highlighted there. That's outliers. Okay. You'd set it up the same way though. X list would be L1, etc., etc. If you have a fancy calculator, you can make the color be blue. But then the last thing we always do, and I could have wrote that over here too, after you set up your box plot is hit zoom 9. Okay. And you can see the regular box plot, bottom left. That's not showing any outliers. And then the box plot on the right, that is showing outliers. So that looks just like the 2 that we made on the previous page. Okay. So good luck. Like my little statistical joke there. Good luck on outliers and box plots. And we will see you later.